Hello, I am Professor Annakkage from University of Manitoba, Canada. This is my third lecture on power system dynamics. This lecture is going to be a very short one, and I will explain briefly how to combine the machine models developed in my previous lectures with the transmission network model. With that, we are able to develop a complete state space model of the power system. In the end, I will leave you with two exercises to explore yourselves. Now consider a branch between node 1 and node 2, and the current in the branch is I12 with its real part equals I12R and imaginary part equals to I12I. So the current equals the admittance of the branch G12 plus JB12 times the difference between voltages at the two ends V1 minus V2, and V1 and V2 are expressed in the same manner as the current as V1R plus JV1I, and V2 is expressed as V2R plus JV2I. We can separate the real and imaginary parts of this equation and write two equations and put that in matrix form as shown at the bottom of the screen. And we note that in this equation there are no complex numbers. Everything is real. Now we can separate the right hand side term into two components like this, separating V1 and V2 on the right hand side, and this gives us the voltage current equation for a branch between any two nodes, in this case node 1 and node 2. Similarly, we can write for a shunt branch, a shunt connected to node 1, the shunt current equals shunt admittance times the voltage of node. Again, separating real and imaginary parts, we can write the equation in matrix form with no complex numbers. Now we are going to use a notation. We are going to define some 2 by 2 matrices and 2 by 1 columns. Yij is a 2 by 2 matrix of conductance and susceptance of node ij, G and B, and the shunt admittance Yish is again a 2 by 2 matrix representing the components of the shunt admittance, and Yii is a summation of 2 by 2 matrices representing the shunt branch and all the other branches connected to that node. Then we define two 2 by 1 column vectors. The current Ii is a 2 by 2 column of its real part and imaginary part, and the voltage Vi is again a 2 by 1 column of its real and imaginary part. Now with this notation we can write nodal equations for the network as shown in this slide. We have on the left hand side a column vector of currents injected to all the nodes, then the admittance matrix times the voltage vector. Now keep in mind that every element of this admittance matrix is a 2 by 2 matrix, and every element of the column vectors, current vector and voltage vector, are 2 by 1 columns. Now if we consider small variations of voltages and currents, and also keeping in mind that the network admittances are constants, we can write for small variations this nodal equation for the network. Now we already have the algebraic equations and differential equations that we developed for the synchronous machine, and with this network model we can combine the algebraic equations of the machines with the network equations and then eliminate currents and voltages from the differential equations to obtain a complete state space model of the power system. I'm going to give you two exercises. The first exercise is a 3-bus example with synchronous generators connected to buses 1 and 2 and a load connected to the remaining bus. And the exercise is to write down differential and algebraic equations for the two generators G1 and G2, and also the network equation for the network. Then combine the algebraic equations of generator 1 and generator 2 with the network equations and obtain the complete state space model of the power system. The second exercise is more advanced, and I don't expect you to do it right away. You have to learn how to develop small signal models of fax devices before you can attempt, and I consider this outside the scope of this series of lectures.